This next lesson involves taking what you know about trig functions. And again, we're working um, oftentimes in radian measure, although you'll see in the word problem, sometimes it's actually not about angular degree, but it will be about something like in the first problem here, which is about time. And now time is going to be on the axis. But still everything you know about how to model with sinusoidal functions, the key features, amplitude, axis, period, k values, etc., will come into play here. So the first thing I'd like you to do then is simply read this word problem and see if you can represent it using a graph. Whenever I draw sinusoidal functions, we're always concerned about those 4 key points. If you remember on the Cartesian plane, 4 key points are when the rotational arm is on the x-axis, then when it's on the positive y-axis, then when it's on the negative x-axis, the negative y-axis, and then back to the positive x-axis. That's one full circle. And so the same thing is true when you stretch this out linearly in a graph, that there are 4 key values that we focus on. So we'll make an axis here. And we want to start sorting out our key values. So as you ride a Ferris wheel, your distance from the ground varies sinusoidally with time. When the last seat is filled and the Ferris wheel starts, your seat is at some unknown height above the ground. So t is the number of seconds. I'm going to label my axis as t here, that you have elapsed since loading at the bottom, and h is your height above the ground in feet. So this axis is the height. The wheel makes 1 revolution every 8 seconds. So 1 revolution every 8 seconds, that's telling us our period. So the period is 8 seconds. And the diameter of the wheel is 40 feet. So we know that the diameter is going to tell us about how high above or below a certain axis it goes. So this doesn't say anything about it being the bottom of the Ferris wheel being any particular amount above the ground. So we're going to, based on this, we're just going to assume that at the ground is going to be 0. If that's the case, then our maximum is going to be 40. Now there are some problems like this with Ferris wheels where they talk about the bottom being somewhat above the ground, which is probably more realistic because the seat actually wouldn't go right down to the ground where this person is sitting, but we're going to just be able to accept that at this point. So now what we need are the key features. If this is 40 and there's no additional height above to the minimum, then halfway here is going to be 20, and that's going to be our axis. So at this point, I'm going to draw an axis in here that we can work with. Now our period is 8 seconds. So we need to draw a So our period is 8 seconds. So we need to label this as 8, and then we're going to split this into quarters. So the easiest way is just to cut this in half and then cut each of those in half. And it doesn't have to be perfect. We are labeling these, so if it's off a little bit, that's okay. So halfway is 4, and then this would be 2 and 6. Now this says that t is the number of seconds that have elapsed since loading at the bottom. So we're going to assume that loading at the bottom is 0. So at the bottom, as we start to make our graph here, at 0, we're going to be at 0. So at time 0, we're at the bottom. Now, all the key values happen every quarter. So if this is starting at a minimum, and we know that there would be no phase shift here because on the y-axis, or in this case the h-axis, it's starting at a typical point for a parent function, in this case a coast function. It starts at a minimum, and so the next step from there would be to go to the axis. Then you would be at a maximum, back to the axis, and finally you end up back at the minimum. And we'll sketch this curve in here. So there's the graph that we were looking for this Ferris wheel application. Now, in any problem that you're going to do, that's really the first step, is to analyze the problem, get the key values that we need, and then to draw a sketch. And then you would be ready to do the next part, which is to solve the problem. So now the problem that's been proposed here is, how high above the ground are you 3 seconds after getting on? So we could look at this graph, and you could go to 3 seconds and estimate. And remember, we started at 0. That's where you get on, is at the bottom. So 3 seconds later, we would look here and we could estimate that. Keep in mind that this graph is just a sketch, and even if we tried to draw an accurate graph without a computer, there's still going to be a fair bit of estimation that would come into play. So this is where we want to write an equation. So now our next step is to write an equation for this. So we're going to finish writing down our key values. The amplitude So we're going to start writing down our key values. The amplitude is 20 because it goes 20 above the axis and 20 below. The axis, which is the C value, is 20. Our K value is equal to the period. And remember, we're going to do these in terms of radians. So 2 pi divided by 8. And then reducing that, we get pi by 4 is our K value. And again, there's no phase shift, so we don't have to worry about the D in this case. Now we're ready to write the equation. So the height is equal to, the amplitude is 20, but this starts at a minimum, so for the A value, it's actually minus 20. Cos of pi by 4 t. Now at this point, all we have to do is put the 3 in. Now at this point, all we have to do is put the 3 in there and calculate how high the person was after 3 seconds. One thing I want to point out is this idea that the axis is t, because we really haven't talked about that before, the fact that we could have something other than an angular measure. It's not degrees, it's not radian, it's times, which is seconds. It's not degrees, it's not radians, it's time, which is seconds. So really what's happening here is when we do this ratio, I'm going to write it out again down here. The ratio is 2 pi radians. Now normally we don't write the radians, but I'm going to write it just to illustrate this. Over 8 seconds. So what you can see here is that this really is a ratio. When we have a trig function, it's expecting an angular measure that represents the angle of it represents an angular measure, which is how far around a circle you have gone. Well, what this is doing is relating how far you've gone around a circle in terms of radians to the time that has passed. So the ratio here is the fact that 2 pi radians represents a full revolution, which is 8 seconds. So when we put time in here, in this case, if we put 3 in here, this ratio basically converts 3 seconds out of 8 to how much that is in terms of 2 pi. In effect, it's going to be 3/8 of 2 pi, which means we're 3/8 around a full revolution. So this is really a good thing to understand in terms of this k value, that really it ends up being a ratio. So now we'll go in and simply substitute 3 in here and find out what the height is. Keep in mind that my calculator has to be in radians. Notice mine's in degrees. So I'm going to make sure and switch it to radians. So I have a button down here, DRG, and so there you can see it's switched it to radians, even though that wasn't my question I was working on. So minus 20 cos of pi over 4 times 3. And so the answer then is 14.4. And so the answer is 14.1. And so the answer is 14. And so the answer is 14.1. Therefore, therefore, you will be 14.1 feet above the ground after 3 seconds. Now, as you can see, all of this work that we're doing is work that you have done before, working with the equations, drawing the graphs here. Basically, the key is to interpret this problem and get to this graph and this key information. Once you've done that, it's all very much work you've done in grade 11 using degrees and now translated into doing this work in terms of radians. So what I'd like to encourage you to do right now is just go ahead and try this problem on your own, and then come back and check and see how you did. So this problem is talking about a pebble that gets in a tire. It says, as you stop your car at a stoplight, a pebble becomes wedged between the tire treads. When you start off, the height of the pebble above the ground varies sinusoidally with the time that the car has been traveling. If the wheel completes 3 revolutions in 3 seconds, and the wheel has a diameter of 35 centimeters, and then we're left with a couple of questions. How high off the ground is the pebble after 1 minute has passed? And in the first 2 seconds, for what time intervals is the pebble above 25 centimeters? So once again, we're going to start by writing down key values and then graphing this. So 3 revolutions in 3 seconds. Means that that's 1 revolution every second. So if that's 1 revolution per second, that means the period is 1 second. Now we can go ahead and start graphing this. So once again, our x-axis, or our independent axis, is t, and that's in seconds. And it says we're dealing with the height of the pebble. And then we see that the maximum height of the pebble is 35. And the axis then is halfway between that because this tire is right on the ground. So there's no shift up that would change the minimum. Otherwise, that would change our axis, but our axis is right in the middle of these. So our axis would be at 17.5, which is half of 35. And then that tells us what our C value would be for our equation. C is 17.5. Now, once again, the pebble here is picked up on the ground. So at time 0, we're going to be on the ground. And then I need to put, before I continue, I need to put my rest of my scale here on this axis. So we know that 1 full revolution happens in 1 second. So that is 1. So we will be dealing with decimal values here. This would be 0.5 seconds. And then cutting those in half again. 0.25 or quarter, and 0.75 seconds. Now I can continue with my graph. Once again, this is a cosine function and it's starting at a minimum. So these two problems end up being very similar. Next quarter, we're on the axis. Next quarter, we're at a maximum. Back to the axis, and then to a minimum. So there's our graph representing the pebble. And now we want to go and solve these problems here. So we need to write our equation. This is height. The amplitude is 17.5, right? We can see that this distance from the axis to here is 17.5 and similarly to the minimum. It's a cosine function. And now I'm thinking about the fact that this is a reflection, so this is a negative, just like in our other problem. And now we need to know what our k value is. So our k value is equal to 2 pi divided by the period, which is 1. And this would make sense that if every rotation is a second, then the k value is just going to be 2 pi, because in terms of circular motion, that's the full revolution is just 2 pi for every 1 second. And this is t. And then our c value, we said, is 17.5. And then we want to use this equation to answer those questions. So the first question is, how high off the ground is a pebble after 1 minute? So 1 minute is equal to 60 seconds. So we want to put 60 in here. And thinking about what I said earlier about the ratios, this makes sense because 60 rotations is going to be 60 full circles, so that's 62 pi's. And so then what we're really putting in this cos function is 120 pi. So we'll put that into the calculator. Minus 17.5 cos of 2 pi times 60, and then plus 17.5. And that gives us 0. And you might be surprised at that at first, but if this is starting on the ground, and we've done we've done 60 full rotations, it's going to be right back where it started. So therefore, after 1 minute, the pebble is on the ground. Now this next problem asks us to determine in the first 2 seconds what time intervals the pebble is above 25 centimeters. So this problem is a little bit more involved. And we only drew this graph for 1 second. So really it would be helpful to have this graph for 2 seconds. So we're going to draw that graph now for 2 seconds. It's easier to draw now because we've already done it once. Now I'm just going to compress it basically. So I'm going to make this 2. Half of that will be 1. And then we'll go from there. So half again, 1.5. Half of this is 0.5. So I have to divide each of these in half again. One 1.75, 1.25, 0.5, 0.75, and 0.25. And I'll add my axis in halfway. $17.5, and this is T, and this is H. The pebble starts on the ground, next quarter axis, next quarter maximum, next quarter axis, next quarter a minimum, and then we're going to carry on next quarter axis, next quarter maximum, next quarter axis, and finally back to the minimum again. So there's our 2 cycles. And it looks a little bit different than our other graph, just in terms of the fact of the scale. If you follow the values, it's still the same graph, just the cycle shown twice. Now, while we're at this, it would be helpful to have a line approximately where we think 25 is to help us think about this problem. So let's put a line approximately, it doesn't have to be perfect, but approximately where we would think 25 would be. And I'm going to label that as 25, and that's going to help us think about the problem. Now, what we're looking for is when this graph is above 25. So we want to know when this equation here is higher than 25. Now, because we have a graph, if we knew where this equation was equal to 25, then we would know that between this point here and this point here, so this time and this time, which we can estimate down here, we could say, well, between those times then, it's above, because we can see that on the graph. So that would be those 2 intervals, and these 2 intervals would be the other ones. So what we're going to need to do here, and this is going to get a little bit more involved now, we're going to take that equation and set it equal to 25. And I would be putting the 25 in here, but it'd be nice to have all of this on the left-hand side, so I'm going to write it that way. Minus 17.5 cos 2 pi t plus 17.5 is equal to 25. So right now we want to know when this is equal to 25, and we're looking for the value of t that gives us that. So in order to solve this, we've learned how to take equations where we have a sine function equal to a value and write a Cartesian plane and then solve it that way. So what we want to do is get the cos 2 pi t by itself. So minus 17.5 cos 2 pi t is equal to, if we bring this 17.5 to the other side, or subtract 17.5 from both sides, that's 25 minus 17.5. Now, if we divide both sides by minus 17.5 to get the cos 2 pi t, now what we have is the cos of 2 pi t is equal to, and we'll work out that value, 25 minus 17.5 divided by minus 17.5. That equals minus 3/7. Now the next step here is to solve that to find t. Now keep in mind that the angle here right now, there's a k value, so this is actually 2 pi t. So the best way to solve a question like this is to simply focus on this whole angle here. So what we want to do is find the value of this whole angle. So to do that, we're going to draw our Cartesian plane. And we're going to represent our values in here. Remember that we need to follow the cast rule. So that's a -3/7. So we need to think about where cos is negative. Cos is negative here. And it's negative here. So there's our triangle. And if we label the sides, we have a ratio there. So if 7 is the hypotenuse, that's adjacent over hypotenuse. So 7, remember, this arm is always positive, or the hypotenuse. And then we have the adjacent being -3, which fits with these graphs. This length here on both triangles is -3. Now what we're doing is the inverse cos of -3/7 in order to get 2 pi t, because remember, we're finding this whole angle right now. Second function, or inverse cos, -3/7. And that gives us 2.01 radians. Let's write down what we have here. Inverse cos of -3/7 equals 2.01. Now what we have to remember is that we need to know whether that's an acute angle or whether that's an obtuse angle, less than 90 or greater than 90, because that tells us whether this is the angle inside of this triangle here, the related acute, or whether we've actually got this angle here. So from here to there is 2 pi, half of a circle. 2 pi is approximately 3.14, and half of 3.14 is approximately 1.57. So that number is greater than 1.57, so that's greater than a 90-degree or greater than an acute angle, so this is obtuse right here. So we have our one answer to here, which is 2.0. So we're looking for these two angles here, and then we have to do 2 rotations. So what we have so far is that 2 pi t is equal to 2.01. Now what we need is this related acute angle here. So that's pi minus 2.01. I'm going to work that out. Pi minus 2.01. And this is our related acute, which is beta. Pi minus 2.01. That gives us 1.13. So that's our related acute. I'm going to write it down in this triangle where I have room. It's the same up in this other one, 1.13. So that means that our other value this value down here is pi plus 1.13. Pi plus 1.13 That gives us 4.27. So now that's our first two values, and now we need two more, right? Now remember, this is not t yet, this is 2 pi t. But we at least know that we have the values we need for the first two spots here where these cross that line, and then we need the next two. So on our graph here, or Cartesian plane, this next value would be 2 pi away from this one, and this next value, if we went at full 2 pi around, that would be the next value that corresponds with that. So basically, to get the next two values, we need to add 2 pi to each of these. So we'll just do that on our calculator. 2.01 plus 2 pi, full circle around, is equal to 8.29. So the next value is 8.29. And then the next value is when we take 4.27 and add 2 pi. And we get 10.55. Now, last step is, and then we'll have t and we'll be able to write our intervals. We need to divide each of these by 2 pi. Now, normally I wouldn't have to show that, and I wouldn't expect you to. You could just go ahead and do the calculation, but let's just show it for the notes here. So all of these are being basically divided by 2 pi to get t. And so we need to do each of those calculations. Zero 0.31 seconds. 4.27 divided by 2 pi. 0.68. 8.2 divided by 2 pi. 1.31. And finally, 10.55 divided by 2 pi. 1.67. Now, before I write my answer, I just want to look at my graph, and hopefully it roughly fits with my graph. So let's look. This line here says that this is 0.31, and that looks about right. This spot here where it crosses is supposed to be 0.68, and again, that looks like it's the right spot. Right here, 1.31 is in the right ballpark on that line. Remember, this is just a sketch, but it's not bad. And then over here, that's supposed to be 1.67. So you can see that those times line up. So we can finally say the statement, therefore, the pebble was above 25. I'm just going to check back what the units were here. Centimeters. 25 centimeters between 0.31 and 0.68 seconds, and 1.31 and 1.67 seconds. So that would be the hardest problem that we've done here, I would say. And keep in mind that there is a problem in the textbook that is similar to this. It's called the Maple Leaf Village problem, and you have to go through a similar scenario. So that's an important problem. All of them are important to do, but that's certainly one you don't want to miss. You might look at it and think it looks difficult and want to overlook it, but come back to this example and follow this in order to do it.